My name is Dr. Danielle Simkus. I work at NASA Goddard, which is just outside of Washington, D.C. on the East Coast. And I'm very excited to talk to you tonight about the OSIRIS-REx mission and my role as a scientist in analyzing samples that are brought back from an asteroid through this mission. So today I'm going to be talking about the OSIRIS-REx sample return mission looking for the building blocks of life in asteroid samples. So I figured I would just start off with a quick introduction to give you some brief information about my background and my pathway to becoming an astrobiologist. Even though I'm working at NASA right now, I'm actually Canadian, and I grew up in a city called Kamloops in British Columbia, Canada. I completed most of my studies at the University of Alberta, which is in Edmonton, Alberta, mainly studying biology and earth sciences, but I soon realized that I was truly passionate about space sciences, and I ended up pursuing a PhD that was focused on the chemistry of meteorite samples. And I finally obtained my PhD and became a space doctor in 2017. And it was the next year that I joined the Astrobiology Analytical Lab at NASA Goddard. And it was just 2 years later in 2020 that I was invited to join the OSIRIS-REx team as a science collaborator. So as I mentioned, I would consider myself an astrobiologist. My background is biology and earth sciences, and I study chemistry, but the overarching theme of my research is astrobiology. And just to define what astrobiology is, it's the study of life in the universe, including the origin, the evolution, the distribution of life on Earth and beyond. So essentially, all the research that I'm doing touches on the question of, are we alone in the universe? Could there be life beyond Earth? And I am an astrobiologist working on the OSIRIS-REx mission. So as Stacy mentioned, the OSIRIS-REx mission has successfully sampled an asteroid, and this mission is returning to Earth next month. So it's actually been going on for several years now. Now, why would an astrobiologist be interested in studying asteroids? I'm going to be talking about asteroids and meteorite samples quite a bit in my talk, so I just wanted to make sure that I defined these terms right off the bat. An asteroid is a rocky body in space. It's a large rocky body. A meteorite is essentially the fragment or a daughter of an asteroid. It's a sample of an asteroid that is naturally landed on the surface of the Earth. So an asteroid is like the parent, and the meteorite is like the son or daughter. And meteorites are, naturally landing on the Earth all the time. An asteroid is the parent body that's currently flying around in space. Why are astrobiologists interested in studying asteroids? Well, some asteroids and meteorites contain organic matter. So what does organic matter in meteorites and asteroids look like? Organic matter can be characterized or described as either insoluble organic matter, or IOM, or soluble organic matter, so SOM. And actually, sometimes 99% of the organic matter in a meteorite or in an asteroid is what we call insoluble organic matter. So that's the green box on the top. It's this very, very complex macromolecular organic material, lots of carbon, lots of hydrogen. It doesn't really have a structure that we fully understand at this point, but it kind of resembles something like kerogen on Earth. The other portion of organic matter in meteorites and in asteroids is soluble organic matter, and this is a much smaller component of organic matter. And these are organic compounds that are soluble in water or soluble in organic solvents, and they're much smaller, as you can see in this pink box below. We are trying to understand what these what these compounds might be, but we do have some information that tells us that there could be millions of chemical structures comprised within this soluble organic matter component. And so for my research specifically, I'm focused on the soluble organic matter. I'm focused on these smaller organic compounds where we can look for individual molecules of known structures. And some soluble organic matter is what we call prebiotic organic matter. So prebiotic just means it's carbon-containing molecules that are essential for life. So these prebiotic organic compounds can be formed by non-biological chemical reactions in space, but we know that they're essential for life. So when we detect prebiotic organic compounds in extraterrestrial samples like meteorites and asteroids, we're not detecting aliens, but we are detecting what we might consider the ingredients for aliens. So the chemical building blocks of life, whether it's us or whether it's life beyond Earth. And this is what I'm most interested in as an astrobiologist. So the early Earth, billions of years ago, was actually heavily bombarded by meteorites and fragments. So meteorites, which are fragments of asteroids and comets. And unfortunately, because the chemical and geologic processes that took place in the early on the early Earth, the record of the origin of life and all the chemical reactions that were going on those earliest years on Earth have actually been erased. We don't have a record of the chemistry on the early Earth. And if we only had Earth samples to study, we would have a difficult time understanding what the prebiotic chemistry of the early Earth might look like. Fortunately, a lot of the asteroids in our solar system are actually relatively unchanged since the early solar system. So unlike the Earth that has gone through all these different geological processes, asteroids have remained relatively unchanged. I mean, we can look at their chemistry and actually study them kind of like time capsules from the early solar system formation. So that's basically what my lab does. We study extraterrestrial samples, specifically asteroids and meteorites. And meteorites are obviously the easiest way to do that. Meteorites are falling onto the Earth all the time. People are going out and collecting them. There's big groups that are specifically organized to go and search for meteorites every year. Meteorites are great to study because they're a low-cost option. We don't need to pay much in order to just pick up a meteorite and then bring it to the lab. But unfortunately, there are some downsides to studying meteorites. There's a high risk of terrestrial contamination, either from the site where the meteorite fell, or when we touch the meteorite, when we pick it up or when we store it, we can contaminate it with those organic compounds that we're interested in. Another downside is that we have lack of sample selectivity. So we can't really be choosy about which types of samples we analyze. And it actually, we find that some meteorites are more likely to survive the entry through the atmosphere, and the process of entering through the atmosphere and burning up, some of them will be more likely to survive. So there's a bit of a bias in terms of which samples actually make it to the surface of the Earth. In addition to that, parent body asteroids are generally unknown. So when you pick up a meteorite, you don't always know exactly where that meteorite came from, what its parent asteroid was. And there's a lack of coordination between analyses. So it's not that common that a bunch of different scientists will come together and study one meteorite with a range of techniques, with a range of science questions, and tackle it together. So OSIRIS-REx is actually a sample return mission. It's our other option for studying meteorites, or for studying these materials. We can just go out and get the samples instead of waiting for them to land on Earth. And we actually end up resolving a lot of these issues that we run into with meteorite analyses. So I'll start with the negative, which is that it's a high cost. We have to send a spacecraft out into space to select samples, but the good news is that we can be highly targeted. We can go and get the exact type of sample that we want. We can be very choosy. We can avoid terrestrial contamination. So we know that our methods are not going to introduce organic matter to the samples. We have well-documented collection and curation. So we know that exactly how the samples were collected. We know exactly how they're stored long-term. And we know the parent body asteroid, so we can look at all these different properties of the asteroid and tie them all together with the chemistry. And we have coordination of analyses. So for the OSIRIS-REx mission, we have scientists coming from all different backgrounds. They all have different science questions, and we're all analyzing the same samples. So we get to basically write a story about this particular asteroid that we're interested in. So as I've mentioned already, the OSIRIS-REx mission is returning samples from a carbonaceous or carbon-rich asteroid. The asteroid that we've decided to target, its name is Bennu. And this is a picture of Bennu, if you haven't seen it before. So Bennu, just to give you some context, is 0.5 kilometer in diameter, which is just slightly larger than the Empire State Building. So it's quite small or quite large, depending on what your expectations are for an asteroid. Why did NASA select Bennu specifically? Well, in theory, NASA could have selected any of the asteroids, of the 500,000 asteroids that are in our solar system. Most of those asteroids are located in the asteroid belt between Mars and Jupiter, but only 7,000 of those asteroids are what we call near-Earth asteroids. So they actually come close enough to Earth. Their orbits are not within that asteroid belt, and they actually orbit very close to Earth, so we could sample them. Only 192 of those 7,000 near-Earth asteroids have actual optimal orbits for sample return. So NASA was looking for a specific type of orbit in order to successfully sample the material. And then only 26 of those have a diameter that's greater than 200 meters. If an asteroid is too small, it might spin too fast, it might be too hard to land on. And then only 5 of those 26 asteroids that had the proper diameter were carbon rich. So NASA was really only able to choose between 5 asteroids that matched all these criteria that we were looking for. And Bennu was actually one that NASA was interested in because it's what we call potentially hazardous asteroids. So it's an asteroid that maybe someday, far, far in the future, could impact Earth. There are lots of asteroids that NASA keeps an eye on, and this is one of those. And so we can learn a lot about asteroid orbits and the potential for Earth impacts by studying this asteroid in particular. So the acronym, you may have wondered where that name came from. It's actually an acronym for the science questions that define this mission. So it's origins, spectral interpretation, resource identification, security, regolith explorer. And origins is the main question or the main science criteria that addresses the questions that my lab group is interested in. So return and analyze material from a pristine carbon-rich asteroid. So we want to learn about the nature and the history of organic matter and minerals within this carbon-rich asteroid. But the mission will also answer a lot of other science questions. So it'll provide ground truth for telescopic data for the entire asteroid population. That's the spectral interpretation part. For resource identification, it'll map the chemistry and the mineralogy of a primitive carbonaceous asteroid. For security, it'll measure the Yarkovsky effect on a potentially hazardous asteroid. So that was just as I was mentioning, looking at the effect of sunlight to see how that might affect the orbit of the asteroid and whether that could potentially push it in a direction that could result in an Earth impact. And lastly, document the regolith at the sample site at scales down to sub-centimeter. And that's the regolith explorer. So the OSIRIS-REx mission actually launched in 2016. So about 7 years ago, September 8th at 7 p.m. Eastern Time from Cape Canaveral. And this is an image from that launch. It spent a 2-year, it had a 2-year journey from the Earth to Bennu. And this launch included included a near Earth ejection, essentially, so a gravity assist. As it orbits around the Earth, it gets kind of a boost and it can travel, that allows it to travel really far to the surface of Bennu. As we got closer to Bennu, which was in 2018, we finally got our first images from the spacecraft. So here is just an example on the left of what we envisioned that Bennu might look like, just based on the telescopic data that we had. And then what was one of the most surprising moments for the mission was when we approached it and saw that it was much different from what we expected, and it's extremely rocky. Just from this image on the right, you can see that there's tons of boulders, tons of pebbles and rocks. That was a surprise to NASA, and it actually just made the science team realize very quickly that there would need to be a lot of care taken in deciding exactly where the spacecraft was going to land on the surface of that asteroid. So a lot of time went into selecting the best site to land, because you don't want to land on top of a boulder, you don't want to have any crashes. So for several months, they were trying to decide between different sites. And this was the site that was selected. It's called the Nightingale site. It's a 20-meter wide crater. It was the least obstructed of the options, so it was the safest spot for the lander to touch down. It was located, or it is located near Bennu's North Pole, so the temperatures are cooler, which means that any of the material, the organic matter, or any of the minerals are well preserved within that area. And it's also a young crater, so it's a freshly exposed area. So any of the material that we're sampling there is relatively pristine. So the sample collection process was actually relatively quick. This took place in 2020, and the lander itself didn't touch the surface of Bennu for more than maybe 5 to 10 seconds. And actually the only portion of the spacecraft that actually touched the surface of the asteroid was the head of this apparatus called the TAGSAM, which is the touch and go sample acquisition mechanism, which you can see in this photo. So it's a big, long robotic arm, and then on the bottom is what kind of looks like a Roomba. It's the tag head. And essentially the arm, as the spacecraft descended closer to the surface of the asteroid, and the TAGSAM head touched the surface of Bennu, the spacecraft released nitrogen gas through that arm, and that nitrogen gas roiled up any pebbles or fine-grained material up into the TAGSAM head. So it's kind of like a vacuum in a sense, and it just brought all that material into the sample collection canister, and then quickly left the surface of Bennu. And this process was extremely successful. It went flawlessly, which I'm sure it was a scary moment for those who were in charge of controlling the spacecraft because of how rocky it was, and just making sure that the TAGSAM head would hit, the proper location on the Bennu surface. So after that sampling moment, the next step was to image the TAGSAM head and just make sure that everything is okay. See what's there. And then the next step was to actually do this spinning maneuver to measure how much material might be inside the TAGSAM head. NASA, or the science team for the OSIRIS-REx mission, defined a set of criteria for mission success. And one of those criteria was that they wanted to make sure that they were getting at least 60 grams of material. So by doing that spinning maneuver, they would be able to determine whether they've reached their goal or whether they've surpassed it. And this is actually an image of the TAGSAM head. And as you can see, it might be difficult to see on your screen, but you can see these tiny little specks. Those are actually all little pebbles, small amounts of material that are flying into space. So when they imaged the TAGSAM head, they actually realized that there was so much material inside this head that they were actually losing material. And it was kind of a bittersweet moment, because that told the team that they, yes, successfully collected more than 60 grams of material, but it meant that they couldn't do that spin maneuver because they didn't want to risk losing more material to space. So they determined in that moment that, yes, we are well above our goal, but the next step was going to be to quickly stow it away and not spin it in space and lose any material. So here's some images of them stowing the TAGSAM head safely into its capsule, which was another nerve-wracking moment for the team. And that went flawlessly, and they were able to close it up, and it was sealed, safe and sound, and those samples are, on their way back to Earth. So this was a moment for the mission control team to celebrate. They finally had the samples in the TAGSAM head, in the capsule, secure, and everything is ready to go back to Earth. And OSIRIS-REx is now on its journey back to Earth. So, the sampling process took place in 2020. It's been almost 3 years now since that happened, and we're looking forward to receiving the samples in just a couple dozen days, less than 40, actually 38 days to go. September 24th is the day that these samples will return to Earth. They will, the spacecraft will release this capsule, and it'll descend onto into the desert in Utah, just outside of Salt Lake City, with a parachute. And this will take place on Sunday morning, September 24th at 9 a.m. Eastern time, so very early for anyone on the West Coast. But it'll be an exciting day for us. It's something that we've been looking forward to for years now, and just watching the live feed of that will be nerve-wracking and very exciting for us. And once the sample has been collected, it'll be quickly transported to the Johnson Space Center, and that's where a curation team, a team of curation specialists are going to open it up and see what's there. And so finally we'll have that moment where we get to see how much material we actually collected and what it looks like. And this is just an image of what we expect it'll look like. This is just a computer image. So once the capsule is opened up and the sample material is observed, and we've measured the mass, and we've looked at, what kind of stones we'd like to analyze first and which ones we'll save for later, the samples will be distributed across our science teams. So we have 25% of the sample material that's going to be distributed to over 200 scientists all over the world, obviously including our lab. You can see NASA, GSFC, Goddard Space Flight Center on the East Coast. And that will take place likely in early October, so just in a couple months. And then the remaining 75% is actually going to be for future scientists. So only 25% will be analyzed right away, and then the other 75% will be stored in special curation conditions so that generations from now, scientists can analyze these samples, which is actually one of the coolest parts of this mission, is that some of the scientists that are going to be able to analyze these samples probably haven't even been born. So we need to make sure that we're saving these samples for when we have better technology and, a better understanding of the chemistry of these samples. And so, yeah, having 75% saved for that is pretty exciting. And as I mentioned several times, we will be receiving samples of Bennu in the Astrobiology Analytical Lab, and I will be one of the scientists in the lab that gets to work directly on the samples through my experiments. So as I've mentioned already, I will be looking for the prebiotic organic matter within these samples using laboratory analyses. So what will happen to a Bennu sample in our lab specifically? I'm just going to walk you through the next few slides just to give you a quick overview of exactly how I carry out the experiments in the lab. So we'll get a chip of Bennu, maybe a gram, maybe less, and we'll powder it up into a very fine homogenized powder, kind of similar to how you might powder up spices or herbs in the kitchen. We actually use a very clean mortar and pestle just to make sure that it's all ground up as well as we can. And then the next step is to extract the organic compounds that we're interested in. So we add water or an organic solvent to our sample so that we can extract those soluble organic compounds that we're interested in. And we make what we call space tea, which is, it's kind of like making tea or coffee. You're interested in whatever organic compounds come out in solution during that extraction process. So we take that liquid or that space tea and we isolate and purify it. So we might remove salts, we might remove sulfur or whatever components of that sample that we need to remove in order to analyze the organic compounds specific that we're interested in. And then we analyze the sample. So how do we analyze those samples? We have techniques that we use. One that I use most often in the lab is called gas chromatography, mass spectrometry. And this is essentially an oven where a sample is injected into as a liquid, and the sample travels through this very, very long column. In the oven, the liquid turns into a gas. So all these compounds are in gas form, and they all travel different speeds through this column depending on their chemistry. And then they, one by one, reach this mass spectrometer or mass analyzer, where we are able to determine which compounds are present, what their chemical formula are, and how abundant they are. Okay, so what molecules do I hope to find through my analyses? I'm going to be doing this gas chromatography, mass spectrometry on these samples. What do I expect to find? Well, my hope is that we will be finding chemical building blocks of some very important biomolecules. So I'm hoping that we'll be finding the chemical building blocks of protein and lipids, DNA, and other biomolecules. So these are organic molecules that we know are essential for life, but we know that they can probably be formed through non-biological reactions in space. And if we're able to study, if we're able to identify these compounds, and then other scientists on the team are collecting information about the geochemistry and the mineralogy of other Bennu samples, then we have all this context to help us better understand the conditions that are most important for forming prebiotic organic compounds. And so as a big picture overview application of our research, we think that these analyses of Bennu samples will greatly advance our understanding of the distribution of prebiotic organic matter beyond Earth. We think that by understanding how these compounds formed in the Bennu samples, we'll have a much better understanding of where these prebiotic organic compounds might be beyond Earth and what that might mean for whether life could form beyond our planet. And that's it. So I just wanted to finish my talk by saying thank you so much for listening.